So now, how do we describe these tracer kinetics? That is, we're going to look at, as I've introduced, I've already stated that we can use first order rate constants. I've introduced the concept of a tracer, and so now we want to see how these first order tracer kinetics, how they can describe the process. So let's start with the situation here. Let's be this our organ. It is mimicked by a beaker full with a fluid. We have a supply tube. We have an exit tube. That's our blood circulation. There is a certain flow going in and a certain flow going out. The water level here of this beaker does not change. The water content of our tissue doesn't change, or the content of the substance doesn't change. Then we will inject our marked molecules, our tracer. The tracer can be also, you can think of it as colored molecules. You can think of it as a dye. You can think of this as a little river. This is a little lake, and this is the river downstream from the lake, and you inject some water dye. And what we're measuring with imaging is what's happening to the color of the lake. And believe it or not, this is what environmental engineers do to understand, for example, lake dynamics. So it's the same principle there. So what we'll do with the experiment is we'll infuse a tracer with concentration CS star. Star means it's radioactive, C is the concentration, and S here is subscript for substrate. That's our substrate. We measure from our beaker here, we measure the sample, and there we measure the tracer enrichment or the specific activity in the tissue. Here C is again for the concentration, T for tissue, and star means the radioactivity. In the case of a lake, this means taking samples, doing the measurement there. In the case of our imaging techniques, this means taking an image and measuring the radioactivity spatially using the imaging techniques that we've discussed the last 2 weeks. Now let's look at when we have a unidirectional chemical reaction from substrate to product T. So we have the concentration of the substrate, we have the concentration of the product, and we have a unidirectional reaction. This means we can only proceed in one direction. And hexokinase is a very good example of such a metabolic system. The product then is being metabolized further by another reaction, and we describe it here with a reaction constant K3. So what we are interested in measuring, or what we are measuring, is this is our compartment here. This is the measurement, the tissue reactivity. And now we'll look at a first order process that converts S into T. And we'll look at the reaction velocity here. Now the reaction velocity is concentrations per mass per time. So it's micromoles per gram per minute. And now the reaction velocity is equals to the rate of change in concentration of the molecule in the tissue, Ct. And this is now given by, with first order kinetics, is given by K1 times the concentration of the substrate minus K3 times the concentration of the product. Here we have used the expression that the rate constant is equals to the reaction velocity divided by the concentration. So if we put that back in here, then we can see here this term is equals to V in, the velocity in, and this is equals to the velocity out, the reaction velocity V out. So K1 and K3 in this context, they are the first order rate constants. They are not true constants because they mimic the situation of the system in a particular state. So they're not really true reaction constants. That's why one also often refers to them as pseudo first order rate constant. For our experiment though, we'll assume that they are independent of concentration and time. The reaction constants have the unit, typically is used per minute, but it can also be per second. Okay, so this is, if we have more molecules entering than leaving, we'll have buildup of the product here, and this will increase. If we have less molecules entering than leaving this system here, we have a reduction of the concentration of this tissue component. Now let's look at what's happening if we are supplying in the substrate CS, we are supplying radioactive molecules. And now we're interested in understanding how the rate of labeled molecules that enters the tissue pool, CT, is calculated. Now the rate of molecules of radioactive molecules here in CT, now just to be sure, it does not have to be radioactive, but we'll just call the term radioactive, or labeled molecules here, is equal to the metabolic flux, that is the flux of number of molecules per unit entering here into this pool, times the probability that one of those molecules is actually labeled. So what this means is, we're saying, we'll take this term here, we have the rate of labeled molecules that appear here is equal to the reaction velocity times the probability they're labeled. This is the number of labeled molecules of CS star divided by the total number of molecules. That's the probability that they're labeled. That gives us the rate of molecules entering CT, and if we plug this in here with this definition here, we'll find that this is equals to K1 times the concentration of labeled molecules in the substrate here, CS. So to give you an example here, we have a hypothetical situation. We have 10 molecules, and now we'll say, okay, these molecules are being supplied at a rate of 10 molecules per minute. That's just an arbitrary number, but to give us something we can easily calculate and we can visualize. So let's say we have 10 molecules per minute that are being supplied. And now the question is, how many of those are going to be producing in the tissue here, the concentration, what is the rate of molecules that are being produced? Assuming that we are supplying here, on this side, we're supplying a total of 10 molecules. So how many molecules, if there are 10 molecules coming here, how many red molecules being produced here? Let's start with the first situation. We have no red molecules entering. Then the rate of product that is being produced is 0. Now you can use here red as a synonym for labeled, just to give it an idea. And one of the problems that we have put together is a situation with colored cars between two cities. So the question is, what is the rate of buildup of labeled molecules? So we're going to have to look here in the calculation here. We're going to have the reaction velocity is 10 per minute times the probability of a molecule being labeled, being red. So if we have 1 out of 10, what is the rate of red molecules appearing in this pool? How many molecules per minute? Well, we have 10 that are coming in. We have 1 of the 10 is red, so we'll have 1 per minute that is being synthesized, labeled molecules. If we have 2, then we have, again, the velocity is 10 molecules per minute. We have 2 out of the 10, so it's 1 over 5 molecules, 20%, that are red, and so the rate of labeled molecules that enters into the tissue pool is now 2. And that's the last example here. So if we have 3, then we have 3 molecules, red molecules entering. We have 10 total, 30% of them are labeled, so we have 3 molecules per minute that enter into our pool. So I hope this example gives you an idea of how to understand how we calculate the tissue, the buildup of tissue radioactivity, its velocity times probability. This turns out to be, with this definition, to be the rate, pseudo first order rate constant times the concentration of the substrate radioactivity. Now what happens if we keep supplying labeled molecules? We obviously will increase the percentage of these molecules that are labeled, that are red. And at some point they will no longer change. And at some point we'll have a significant number of red molecules that leave this pool. So we need to add this efflux, this reaction rate, to the calculations. Now what is the percentage of red molecules that are leaving this pool here? It's equal to the metabolic flux times the probability of this molecule being labeled. So it's the flux, here this is the flux, times this term here. Now we just put CT star over CT. And so we get here, by taking this plus this for applied to this pool, we're now obtaining the efflux term, and that's minus K3 times the tissue activity of the tissue pool as a function of time. And this is essentially the system of a linear differential equation that describes the rate of change of labeled molecules appearing in the tissue pool as a function of the radioactivity or the tracer in the substrate, that is the blood pool. Okay, so now the question is, how do we describe this one tissue compartment model? What are some of the features? I'll recap here the model. We have the substrate, we have the influx reaction, that's described by the reaction constant K1. We have the efflux reaction, described by the reaction constant K3. We have the two concentrations in the tissue pool, and we just established the equation that describes the rate of change in labeled molecules in the tissue as a function of the change in labeled molecules in the substrate, for example, in the blood or the precursor. So this is a linear differential equation. It's a first order linear differential. It's a linear first order ordinary differential equation, and this can be solved mathematically by using the Laplace transformation. The solution then is given by the tissue radioactivity. The tracer in the tissue is equals to K1 times the precursor, the CS star here, as a function of time convoluted with e to the minus K3t. Mathematically, the convolution is this mathematical operation, and so this is in principle the solution that we can obtain. So mathematically. Now the Laplace transformation is not a very easy algorithmically not very easy to handle. It is not very intuitive, and actually in practice it is hardly being used, although this is strictly speaking the mathematically strict solution. So I want to illustrate a simple example first. This example is very simple because it also makes us understand a few important features. So we'll take this example and we'll assume that we have done an experiment where we raise the activity, the tracer concentration in the blood or the precursor at time 0 from 0 to a value alpha. We'll call it alpha. We can call it anything that we want. So if we look at the concentration of CS star, the labeled molecules, the tracer, at time 0 it goes from 0 to alpha, and then we assume it is constant. So this is a very simple situation. Now we can write the above equation here. So we'll take for this situation, we'll write the equation, and we'll see at times 0 or higher, what is happening is that the tissue concentration of the substrate of the tracer is equals to K1 times alpha, because then we have set now this concentration to constant, minus K3 times the tissue concentration of the tracer. And this is something we can mathematically handle ourselves. So we got on the left side, we got a variable, Ct star, that is the time derivative. And on the right side, we got the same variable. And typically when we have the derivative on one side and of a function and the function on the other side, well, this basically means we're looking at something where the derivative of the function is equal to the function times some constant. And the solution here involves, therefore, the exponent e to the minus something. And one can do the ansatz. I won't go into the mathematical details here, and I'll just give you the solution here. So, and this you can verify by plugging this expression that we have here into this differential equation and solving and verifying that this is indeed a proper mathematical solution. Now, what does this imply? Well, if we take this function and we evaluate it at time 0, so we set t to 0, this term becomes 0, then the tissue radioactivity at time 0 is 0. That makes sense because we have said we start out with nothing, so there's nothing in the tissue, and at time 0 we jump to alpha in the precursor. That's this term here. Now what's happening at time infinity? The tissue radioactivity will exponentially approach a constant value, K1 alpha over K3. So we're getting an exponential increase, or if you look at it from your side, an exponential increase to a plateau level with time. So I'll have schematically drawn this here. We have time on the x-axis, the tracer enrichment On the y-axis, what we'll see this function is an exponential increase with time. And we're getting the plateau enrichment. Or to illustrate this here, we have an injection of a tracer. This is an illustration from a brain experiment, and the brain will change color as the tracer is appearing in the tissue and labels the tissue concentration. Now, conceptually, what we need to get our metabolic rate, this is described by the parameter K3. So we need to determine this parameter K3 here. And we might think that for such a simple function, an exponentially increasing function, e to the minus, asymptotically going to a steady state value, but this is mathematically very simple. It actually turns out this is not as simple in practice, and there are one has to be a bit cautious here. For one thing, to determine this time constant, one needs to know when the plateau enrichment is achieved. If we don't measure to the plateau enrichment, we don't have a good idea where the plateau enrichment is, and so this constant K3 is actually practically not very well determined. So it depends strongly on whether we know what this steady level is, so that we can estimate from the fitting process the rate at which the enrichment is achieved. If we have a fast metabolic rate, it happens like this. If we have a slow metabolic rate, it happens like that. But to get a fairly precise estimate, we need to have a good idea on the plateau enrichment. And this is essentially to any function that has this form is a mathematical feature there that we have this term, the steady state enrichment, and this term, the rate at which it achieves steady state. Mathematically, when you fit this to the time course, they are correlated typically with very negative correlation coefficients. So this is one of the difficulty, and we'll be seeing more of these equations in the second course on MRI. The measurement of metabolic rates depends on our knowledge what's happening in the substrate, so in the precursor pool, CS, relative to the tissue pool. And we have just worked with a simple example where what is happening in the blood was assumed to be a step function. But let's now look at what is this input function, this what's happening in the blood in reality. So we'll take an example of a practical example. We'll infuse this tracer with a so-called intravenous bolus infusion. This basically means we'll take the syringe, we'll inject the tracer into the bloodstream in a relatively short time. That's what the bolus means. Intravenous, obviously, into the veins, so it's very fast application. So the tracer goes into the vasculature in a short time as a bolus. Yes, and this does involve needles, so if you're queasy about needles, this is not the technique you want to expose yourself to. Then what happens is this tracer that goes in a very short time, we'll assume it's very short, undergoes mixing in the circulation. So this is, we'll assume here it's well mixed with the blood, so this involves the heart. Then the substance can undergo exchange with, say, interstitial spaces or even intracellular volume. So this happens in the circulation. So, and as a result of this process, instead of getting a bolus where the tracer appears, is very high for a short time and then again zero, what we'll see in the blood is a rapid rise of the tracer and then sort of a relatively slow decay, so dispersion due to these mixing processes. And that's what is then measured typically in the artery. It's the measurement of the tracer in the arterial plasma, and this is what we call the arterial input function, or CS star. So if we look at the tracer in arterial blood, this is a typical tracer here, concentration, this is in decays per second per milliliter or kilobecquerel per milliliter over time. So we have the rapid injection, we get the bolus, and then relatively rapid reduction. What then happens as the second step is that the tracer is distributed to the capillary bed and then undergoes exchange with the tissue. So the uptake into the tissue involves perfusion, it involves permeability of the endothelium, it involves the blood volume as a factor, it involves transport across cell membranes, possibly specific binding to receptors, or non-specific binding, or enzyme activity. So these are all factors that influence the ultimate uptake of the tracer in the tissue. So as we have given our bolus here, we're getting a sudden increase in tracer. We're also getting a concentration increase in tracer in the tissue due to extraction from the blood. And if we now look at the output, so this is the tissue radioactivity here. We have the concentration in tissue on the y-axis, the time on the x-axis. Then this is what we are seeing, the concentration that we can measure with the imaging techniques. That's the black line here. This particular graph here is a simulation of a metabolic process where multiple compounds are involved. Red and green are just some intermediate other compounds that contribute to the overall tissue radioactivity, since we cannot distinguish chemical species based on their X-ray activity alone. We have, of course, this tracer is not going to stay in the tissue. There are backward transfer. We take, for example, oxygen. If you have oxygen, you breathe oxygen, it's converted to H2O15, and this H2O obviously then at some point leaves the tissue again. And for glucose, if you take up glucose, you look at C11 glucose, for example, this will ultimately leave the tissue in the form of CO2, C11 labeled CO2. So the backward transfer is can be in the same species or can be a different chemical species, but this ultimately reduces the concentration of the tracer in the tissue.